In today's class, we will discuss what is an oscillating electric dipole and the radiations emitted due to an oscillating electric dipole. In an high school level itself, we are introduced to what is an electric dipole. An electric dipole is nothing but it is a configuration of two equal and opposite charges separated by a very small and finite distance. If we take q to be the magnitude of the each charge and dl is the distance of separation between the two charges, then the dipole moment can be counted as p equal to q into dl. And the direction of the p is from minus q to plus q. That's along the line joining the two charges. In case if the charge varies sinusoidally, the dipole moment will also vary accordingly. So that is, the charge q can be written as q naught into e power minus I omega t. Then the dipole moment p can be written as q naught e power minus I omega t into dl, where this q naught into dl can be written as p naught. So p is equal to p naught e power minus I omega t. If a dipole whose moment varies sinusoidally is called as an oscillating dipole, we can assume an oscillating dipole to be equivalent to an accelerated charge distribution, and its dipole moment is also equal to a dipole moment of an oscillating dipole. For such cases or for such distribution, the dipole moment P is given by integral of rho r dv prime. The time rate of change of dipole moment then can be written as P dot is equal to dp by dt. So we know the value for P, it is q dl. So it is dq by dt into dl. We know the value for dq by dt as the current. So P dot is nothing but it is equivalent to the current element IDL. So this expression shows that the time rate of change of dipole moment of an oscillating dipole is equal to the current element. So if an oscillating electric charge of dipole undergoes an acceleration, and we all know an accelerated charges will always emit radiations. So therefore an electric dipole also radiates energy. Now let us calculate the amount of radiation emitted by an electric dipole. For this, let us have a configuration like this. A dipole will consist of two charged spheres located along the z direction at a distance plus dl by 2 from the origin, and they are connected by a wire of very negligible capacitance. Also, let us assume the length of the dipole ds is very small compared to the length or the wavelength lambda of the radiation emitted due to the periodic oscillation of the charges. So which means that all the source points have same retarded time and no phase difference occurs at the observation point P between the waves originating from different parts of the source. So we have a point P at a distance r from the origin, that is the point of the observation, and this point can be very well written in terms of the spherical polar coordinates r, theta and phi. Due to the axial symmetry, the phi has no meaning here, or phi has no dependence here. Let us now first compute what is the vector potential A due to this current distribution. In general, the vector potential due to a current distribution is given by A bar is equal to mu naught by 4 pi into integral of J by R dv prime. Here the square brackets represents the retarded time is considered here. So we know integral of J dv prime is nothing but it is the current element ideal. So A can be written as mu naught by 4 pi r into P dot. So from equation 1 it is very clear the vector potential A depends upon only the value of r, that is r component, and it varies as 1 by r, which tells or which reveals that this vector potential A is independent of theta and phi, and the direction of the vector potential is always that of P dot, which indicates that vector potential is always parallel to the z axis or the polar axis. If n cap is the unit vector taken along the polar axis, then we may write the unit vector n is equal to nr cos theta minus n theta sin theta. So now equation 1 can be altered and written as A is equal to mu naught by 4 pi r P dot nr cos theta minus n theta sin theta. Then writing A in component form, A r nr plus A theta n theta plus A phi n phi is equal to mu naught by 4 pi r P dot cos theta nr minus sin theta n theta. Equating the components of A in each side, we get AR is equal to mu naught by 4 pi P dot cos theta by r, A theta is equal to minus mu naught by 4 pi P dot sin theta by r, and A phi is equal to 0. Next, let us find the scalar potential phi. For a free space, we know the Lorentz condition is given by div A plus mu naught epsilon naught dou phi by dou t equal to 0. Writing mu naught epsilon naught as 1 by c square and rearranging, we get dou phi by dou t is equal to minus c square div A. Then let us write the divergence of A in spherical polar coordinates. So we get minus c square into 1 by r square dou by dou r square AR plus 1 by r sin theta dou by dou theta A theta sin theta plus 1 by r sin theta dou A phi by dou phi. So we have the value for AR A theta. So substituting those values and simplifying, we get minus mu naught c square by 4 pi 1 by r square P dot cos theta plus r cos theta by r square dou by dou r P dot minus 2 by r 2 cos theta by r square into P dot. But the retarded dipole moment P dot can be written as P dot into T minus RC. So dou by dou r of P dot is equal to minus 1 by C P double dot. So substituting in place of dou by dou r by dou P dot, so equation 4 becomes dou phi by dou t is equal to minus mu naught c square by 4 pi 1 by r square P dot cos theta plus r cos theta by r square into minus 1 by c P double dot minus 2 cos theta by r square into P dot. So which on simplifying and substituting the value, mu naught epsilon naught is equal to 1 by c square and dou by dou t of P cos theta plus r square plus P dot cos theta by rc is equal to cos theta by r square into P dot plus cos theta P double dot by rc. In the above equation, we get dou phi by dou t is equal to 1 by 4 pi epsilon naught dou by dou t into P cos theta by r square plus P dot cos theta by rc. So on integrating this, we get phi is equal to 1 by 4 pi epsilon naught P cos theta by r square plus P dot cos theta by rc. So from the above equation, it is clear that scalar potential varies as cos theta, which indicates that the scalar potential phi becomes 0 in the equatorial plane where the potentials due to the two charges cancel exactly, which means at equatorial plane the value of theta is 90 degrees. So cos 90 degree is 0, which means that the potential obtained due to the minus q charge and the potential obtained due to the plus q charges are equal in magnitude but opposite in direction. So they cancel out at the equatorial plane. And the scalar potential consists of two parts. One varies as 1 by r square and other one as 1 by r. The first term is dominant for the small values of r and hence this term is responsible for induction field in the nearby zone, while the second term dominates for the values of larger values of r, and hence this term is responsible for radiation field in the distance zone. So now we have computed the values of A and phi. With this knowledge of A and phi, we can very easily calculate B and E. So we know the B can be written as del cross A and E can be written as minus dou A by dou T minus grad phi. Now let us calculate the magnetic field induction, which is given by B is equal to del cross A. So curl of the A can be written in spherical coordinates as 1 by r sin theta into dou by dou theta A phi sin phi minus dou theta by dou phi into nr plus 1 by r into 1 by sin theta dou A r by dou phi minus dou by dou r r A phi into n theta plus 1 by r dou by dou r r A theta minus dou A r by dou theta into n phi. We know the dependence of phi, A phi is equal to 0 and A theta A r are very independent coordinates of phi. So therefore B reduces to 1 by r into dou by dou r into r A theta minus dou A r by dou theta into n phi. We have the values for A, r and A theta, and substituting and simplifying we get B is equal to 1 by r into minus mu naught by 4 pi sin theta minus p double dot by c plus mu naught 4 pi r p dot sin theta into n phi, which on simplifying we get B is equal to mu naught by 4 pi p dot sin theta by r square plus p double dot sin theta by r c into n phi. So from the mathematical expression of B, we can say the magnetic induction varies as sin theta. So this indicates that the magnetic induction B is minimum along the axis of the dipole and maximum along the equatorial plane. This is because sin 90 degree is 1. So sin will have the maximum value at the equatorial plane. So the magnetic induction is maximum along the equatorial plane. The magnetic induction B contains two terms. So one varies as 1 by r square, other one as 1 by r. So the first term dominates for the small values of r and it is responsible for the induction field produced there, and the second one is dominant in case of the larger values of r, hence we call this term is responsible for the radiation field. So we can write B induction as mu naught by 4 pi p dot sin theta n phi. We have already proved that P dot is equal to the current element ideal. So which simply reduces to mu naught by 4 pi ideal into r cap by r cube, which is nothing but the famous Barth-Savart law. And we can write B radiation as mu naught by 4 pi p double dot sin theta by rc into n phi. Next let us calculate electric field strength E, so which can be written as minus gradient of phi minus dou A by dou T. So this can be written as minus dou phi by dou r into nr plus 1 by r dou phi by dou theta into n theta plus 1 by r sin theta dou phi by dou phi n phi. So putting the value of dou phi by dou theta and everything and rearranging, we get dou p cos theta 4 pi epsilon naught r square into nr plus p sin theta by 4 pi epsilon naught r square n theta plus 2p dot cos theta by 4 pi epsilon naught r cube c into nr plus p dot sin theta by 4 pi epsilon naught r square c into n theta plus p double dot by 4 pi epsilon naught r c square sin theta n theta. So we can see E consists of three parts. The first part falls off as 1 by r cube and it is very dominant over other parts only at small distances. So this part represents only the static field of an electric dipole. So we can write E static is equal to 1 by 4 pi epsilon naught 2p cos theta by r cube into nr plus p sin theta by r cube into n theta. And the second part depends upon P dot or the current I, which arises due to the steady currents. So that this part represents the induced field and it falls off as 1 by r square. So we can write E induction is equal to 1 by 4 pi epsilon naught 2p dot cos theta by r square c into nr plus P dot sine theta by R square C into n theta. So, and the third part depends on P double dot and falls off as 1 by R. So, this is a dominant at a very larger distances, and this field represents the radiation field. Thus, we can write E radiation is equal to 1 by 4 pi epsilon naught P double dot sine theta by RC square into n theta. So, with all these knowledges of E radiation and B radiation, we can very easily compute the Poynting vector and what is the amount of our average energy flow due to an oscillating electric dipole. So, the energy flow takes place due to the radiation fields, which is given by E radiation and B radiation. Therefore, we can write the Poynting vector as S is equal to E cross H. So, in place of E, we can write E radiation. H can be written as B radiation by mu naught. We have the values for E radiation and B radiation, substituting in it and simplifying. So, simplifying, we get the time averaged Poynting vector as P naught square omega power 4 sine square theta into nr divided by 32 pi square epsilon naught c cube r square. So, this expression represents the average energy radiated per second per unit area in a normal direction by an oscillating dipole. So, we can see the expression depends upon sine theta. So, if it depends upon the sine theta, the values of the energy flow will be maximum along the equatorial plane, that is when the sine is at 90 degree. So, the time average Poynting vector varies as sine square theta. This means that the flow of energy is 0 along the dipole axis and the maximum along the equatorial axis. 0 along the dipole axis means when theta takes 0, well, sine becomes 0. So, the average energy also goes to 0 and the average energy is maximum along the equatorial axis. Next, let us calculate what is the power radiated due to an oscillating dipole. So, the average power radiated per unit solid angle is given by dP by d omega, that is the solid angle. So, the S average into 4 pi r square divided by 4 pi the solid angle S into r square. So, dP by d omega is equal to P naught square omega power 4 sine square theta 32 pi square epsilon naught c cube. So, to find the total power radiated, we can integrate the above equation for all angles. So, integral dP by d omega into d omega. So, it is P naught square omega power 4 by 32 pi square epsilon naught c cube into integral of 0 to pi into integral 0 to 2 pi sine square theta d theta into sine theta into d phi. So, and on simplifying, we get P naught square omega power 4 by 12 pi square epsilon naught c cube. And splitting and writing, we get 1 by 4 pi epsilon naught p square omega power 4 3 c cube. So, this is the total expression for the total power emitted. So, from the above equation, it is very clear the total power radiated by an oscillating dipole is proportional to the fourth power of the frequency omega. So, we can come across this electric dipole radiators in the emission of an radiation by an excited atoms and the electromagnetic waves transmitted by antenna. So, these two are the very best examples of electric dipole radiators.